How can we use heat to do work? Well, let's find out. So here's an idea. If you notice over in the upper right here, there's an enclosure with some gas in it. So gas in an enclosure, it's really just particles bouncing off the walls. The temperature of the gas in the enclosure is proportional to the energy. The more the temperature, the higher amount of bouncing. When particles hit the walls, it puts a force on the walls. You can see that over here in the red arrows on the outside of the walls. Every time a particle hits, it puts a little force on the walls. The average force per unit area on the walls is called the pressure, P. A constant temperature, as the volume decreases, the pressure increases. So if you were to squeeze the walls inward, the pressure would get bigger. The more particles that you put into the enclosure, the higher the pressure will be, if you keep all other things the same. Or the volume has to get bigger if the pressure stays the same. Or it's possible that both the volume and the pressure get bigger. So that brings us to the ideal gas law. PV equals N times the Boltzmann constant, K sub V, times the absolute temperature in Kelvin. Boltzmann constant times the temperature in Kelvin essentially converts the temperature to units of energy per particle. And capital N is the number of particles. So the right-hand side of the equation is the amount of energy in the particles in the gas in the enclosure. And as you notice, as you increase the temperature, it increases either the volume or the pressure. If you increase the number of particles, it increases either the volume or the pressure. If you keep the temperature and the number of particles the same and you increase the pressure, that would come from a decrease in the volume. If you increase the volume, it makes the pressure go down. This is the ideal gas law, sometimes known as PV equals nRT, where R is the Rydberg constant. So anyway, now how are we going to use this to get work? Well, work is a force moving something. So if you think about the pressure on a wall, let's think about the top wall. The pressure on the top wall times the area of the top wall is the force on the top wall. So there's a force pushing the top wall up. What if we exchange that top wall for a piston? Like this, where the piston weighs something, and we've got then gravity pushing the piston down. But on the bottom, the gas inside the container, represented by this one little particle, or one big particle there in orange, is bouncing around, and it's pushing back against gravity. And the place that the piston settles into, known as the equilibrium position, is right there. However, if we were to try and make this pressure that's pushing the piston up actually do some work, it would have to actually move that piston. So in order to move the piston without adding particles, the thing to do would be to increase the temperature right here. So if we do that, if we change T to T plus delta T, we now have N is KB times T plus delta T. And so if you make the right-hand side of the equation bigger, the left-hand side has to get bigger. Now the pressure isn't going to change because the force on the piston isn't changing, so the pressure is still the same. The same pressure is needed to hold the piston, the pressure doesn't change because it's coming from the gravity actually. But the volume then therefore has to change, so the volume gets larger. And that means work was done because you pushed the piston up. So how can we change the temperature? Well, let's add heat. That's the last thing, when I wanted to get warm, I added heat. So here's some heat. When you add heat, what that does is that increases the temperature inside of the particles in the gas inside the chamber, and they start bouncing around even faster than they were before. When they bounce around faster, that moves the piston up, because we need more volume in order to reach equilibrium according to the ideal gas law. So in other words, work happens because the force from the pressure of all those hot particles push the piston up. Now, for this to happen, heat had to flow from the candle into the gas. And for heat to flow, you have to have it flow from a hot source to a cold source. That means that the candle had to have a hotter temperature or more energy, than the gas. If we don't add heat, then the temperature remains the same, and if the temperature remains the same, the piston doesn't go up. So there's no motion. And of course, then no work. So in order to have work, we have to have a difference in temperature. In other words, we have to be able to create a temperature, or we have to have a source of heat that has a higher temperature, which is the candle, than the gas that we're trying to heat up. Makes sense? So now what I'd like to do is think about how that all happens. So the candle actually has to have a bunch of chemical energy all bunched together. It needs to be all together. It can't be spread out over the universe. We have to put it right underneath the pressure vessel. When the candle burns up the energy, that energy that it burned up is spread out all over the world. In other words, you see the hot gases from the candle, they go up and around the container and eventually get out into the atmosphere, and you end up with no candle. When you're done, it's all burned up. And all that energy that was in the candle is now spread out all over the place. And as time goes on, with the candle, as more and more of the candle is burned up, more and more energy gets spread out over the universe. And eventually, the candle actually burns up, and you're not going to get any more energy from that candle. And so you can't do any more work because your candle is gone, and you can't do work. The other thing that happens is it's possible that the temperature of the gas gets hot, and it gets to the same temperature, as the candle, and then when it gets close to that, then you're not putting very much heat into the gas, and it doesn't do any more work for you. So essentially, a spread outness, what happened to the candle, is something called entropy, and that's something for my next video.